Good morning, everyone. Today we'll discuss on the life mode of bivalves. Every organism they are try to adapt to their surrounding environments so that they can live in a better way. That means they can provide better and better solutions for the environmental demands, and to fulfill those demands, to they have to provide better solutions, and for that they have to develop certain functional morphologies, certain adaptation characters, so that they can live successfully. That means they can adapt to their respective environments. Now, bivalves as a aquatic organisms, they are also diverse and living in different environments. So thereby different problems, different environmental problems, and that they solve in their own way. Now, due to this different way of solving in different bivalve groups living in different environmental conditions, they have shown different morphologies which indicates their different mode of life. Now, in this picture, you can see different size and shape of bivalves which are indicating their different mode of life. That means they are different environmental condition where they live. Now, if we try to divide the living environmental condition of bivalve in a broad way, we can divide them into two groups. The first one, that is the epifauna, which lives above the substrate, above the sediment surface, and the second group, that is infauna, which lives within the substrate, that is within the sediments or within the rocks. So broadly there are two groups, epifauna and infauna. Now, depending on this epifaunal and infaunal nature, there are altogether 7 major mode of lives found in bivalves. The first one is infaunal shallow burrowing, second one is infaunal deep burrowing, then epifaunal attached by byssus. These are some kinds of threads by which the bivalve is attached to the substrate. Fourth one, epifaunal attached by cementation. Fifth one is free lying. Sixth one is swimming. And the last one, that is also infaunal, but they are boarding or cavity dwelling. Now we will come one by one in detail about the mode of life. So this is a schematic diagram showing the positions of bivalves in different conditions. That is, some bivalves live epifaunally above the sediment surface, and some lives within the sediment surface, that is infaunally. Now, to start with the life mode of bivalves, we start with the infaunal mode of life, that is firstly the burrowing mode of life. Now, the burrowing mode of life involves the bivalve to burrow or to dig within the soft sediment. Now, this burrowing process is not a easy event. It requires few steps to dig within the soft sediments. Firstly, the bivalve have to raise its foot downwards and swells the food with blood from the circulatory system, so that the food soft, that is the soft mass, it gets some kinds of fluid covering, or it becomes a little slippery, so that it cannot be injured during insertion to the soft sediment surfaces. In second stage, the bivalve close or take in its siphon within the shell. In third stage, the previous process processes are followed by rapid adaptive movement of the two valves, that is the bivalves rapidly clapping its two valves, and this clapping dilates the surrounding sediments of the food and squeezes water out from between them. So basically, dilates or it loosened up the digging portions sedimentary cover so that the bivalve can easily penetrate or easily go inside the sediment surface. In the fourth stage, the foot is retracted and the cell sinks down into the sediments. So in this stage, basically the foot extended inside the sediment cover, and after that uh, it fixed its foot and dragged the rest of the shell towards the forward direction. Then muscle relax, and at this way the next cycle starts. So it's not just a single cycle. These stages or these steps are followed repeatedly, and by this, through successive cycles of these steps, the bivalve can go inside the sediment cover. Now here you can see a bivalve. This is found in the east coast of India, where you can see a bivalve is starts burrowing. You can see the repeated cycles. By repeated way, slowly the bivalve is going within the sediment inside. It becomes infaunal. So as I already told, the bivalve extend its foot and stretched its foot at the long distance, and after that it fixed its foot and dragged the rest of the shell towards the following direction, and it's happened in repeated cycles, and by repeating the processes one after another or several times, the bivalve ultimately becomes infaunal, that is, it becomes successful to go inside the sediment body. Now, an interesting feature in the all infaunal bivalves, that means all the bivalves which lives infaunally, which lives within the substrate, is found that in all these infaunal bivalves, if you closely look, the orientation or the direction of hinge line and muscle line, or you can say the anteroposterior line, you can see in all infaunal bivalves, the hinge line and muscle line are parallel to nearly parallel. So that is a characteristic feature by which we can identify all the infaunal bivalves, whether it may be a shallow infaunal or a deep infaunal or even a borer. So for all infaunal bivalves, any kind of infaunal bivalves, the hinge line and muscle line will be always parallel or nearly parallel. Here you can see bivalves. One is infaunal. You can see that it partially goes down within the sediment cover, and here you can see a bivalve which is epifaunal, that is lives above the substrate. In this case, the hinge line and muscle line are parallel, and in this case you can see that the hinge line and muscle line makes an angle. They basically cross cut each other and makes an acute angle. And interestingly, these two bivalves are very closely related, but because although they are closely related, but because of their different life position, the different life mode, one is uh, relatively infaunal and other is completely epifaunal, they show, or their cell morphology changes. They show some different uh, positions of different organs, like the muscle scars, like the orientation of hinge line. So whenever these epifaunal bivalves its relatives becomes infaunal, then only its orientation of muscle line and hinge line are changed. So again, as I already told you, that whatever infaunal bivalve it was, it always shows parallel orientation of hinge line and muscle line. Whereas in case of epifaunal bivalves, these two makes some angles. That is the two lines, hinge line and muscle line, they cross cut each other. Now coming to detail about the functional morphological characters for each mode of life of bivalve. So to start with the shallow burrowing bivalve, that means what are the morphological features by which we can identify this mode of life within a bivalve specimen. For shallow burrowing bivalves, they live in a shallow depth within the sediment cover. So their shell is equivalve and equilateral to slightly inequilateral. There should be two adductor muscle scars. That means they must be dimerian, and these muscle scars may be isomerian or weakly anisomerian. So here, as you can see, that these there are two muscle scars. One is here and this here, and they slightly differ in size. So you can tell them that they are weakly anisomerian. That is not very pronounced in difference in size. As the bivalves is shallow burrower, so to maintain contact with the external water body, external aquatic body, to get food and to excrete the uh, to remove out the excreta within the uh, water environment, it requires a short siphon. So thereby the indicative of soft siphon in the shell is in form of short pallial sinus, or sometimes even it happen that the pallial sinus is almost absent. Now when pallial sinus present and when absent, I'll come later. Next, cell may be thick, it should be fairly ornamented, and it's not very elongated. It also have a high width, as you can see in this picture, because it have to go a shallow depth within the sediment surface. So for that, they only have to displace a little amount of sediment from to make its place, to make its position within the sediment surface. So they did not have, or they did not much face much problem if they have this large width. And as they are infaunal, so their hinge line and muscle line are parallel. So if a bivalve specimen fulfill these characters, that means we can identify these characters within a bivalve shell or within a fossil bivalve specimen, we can identify that it's living in this uh, in a shallow burrowing environment, or the mode of life of the bivalve is shallow burrowing. In a shallow burrowing bivalves, as I already told, that sometimes there are the bivalve specimen lacks any siphon. Now here you can see one bivalve is going into the sediment surface, it digs, it enlarge or it extends its foot within the sediment cover and drag the rest of the cells within the sediment cover, and thereby it just feed at the sediment water interface. So this below portion, this portion is basically sediment, and this above portion is basically water. So it just exactly fit in the sediment water interface. Now interestingly, you can see that the posterior margin of this bivalve is become flat, so that neither portion of the bivalve remains out from the sediment water interface. Now, to hide itself from its enemies, if the suppose the bivalve have these kinds of angular posterior margin, so it has to dig more sediments to completely becomes infaunal, Otherwise, this portion of the bivalve remains out above the sediment surface. So it becomes visible to its predators. That means its enemies or its predators can sense it and they can injure or they can kill this bivalve. So to remain infaunal without any siphon, these bivalves modify its posterior margin to this flat shape. Now, with the help of this flat shape, the bivalve can bring or the bivalve brings its posterior margin parallel to this sediment water interface line or sediment water interface plane. Now the bivalve, without digging much inside the sediment cover, it become infaunal, and it can also hide all of its sides from its enemies. Now, as it is occurred in the sediment water interface, so just by opening the two valves of the bivalve shell, it can directly get the fresh nutrient rich water, and also it can expel out the excreta rich water into the aquatic environment. So thereby the bivalve does not need any siphon to maintain contact with this water environment. Just by opening the two shells, it can directly get fresh water and it can also expel out the extra rich water. So that is why these are the shallow burrowing bivalves lives in sediment water interface, and for that they did not have siphon, and due to this they have to modify their posterior margin to something flattish areas or flattish portion. Now, there are some semi-infaunal bivalves. That means these bivalves are not completely goes inside the sediment cover. That is, some part of the bivalve remains out above the sediment water interface, as you can see in this picture. So here you can see the sediment surface, and you can see the posterior part of the bivalve remains out above the sediment water interface. Now, how did you identify these kinds of bivalve? These have exactly similar feature like of a shallow burrowing bivalve. So they have thick shell, high width, more or less triangular shell, not very elongated, having shallow pallial sinus, nearly isomerian to weakly anisomerian muscle scars. So all the characters are more or less similar to shallow burrowing bivalves. Only thing by which you can identify is the presence of these epizoans. These are one kinds of parasites which lives on the shells or on the surface of some other organisms, like these barnacles. These are known as barnacles. These are one kind of epizoans. They, in their from their larval stage, when they settle in the sediment bottom or sediment surface, they settle over the shells of this bivalve. Now, as the posterior portion of the bivalve is open in the aquatic environment, so all the larvae of these barnacles settle in the posterior portion of this bivalve, and thereby, if you see the attachment of these barnacles in the bivalve cell, they all occur in the posterior side, all occur. Now, if the bivalve is in living conditions, so then the bivalve will not allow the barnacles to settle over the posterior commissural line. That means along this line, the bivalve will not allow these epizoans to settle and fix in this posterior commissural line, because if a epizoan barnacle attached in this posterior commissural line, then the bivalve will not allow, or the bivalve will not able to open its two valves, because it is fixed, it is sealed by the epizoan attachment. So during living condition of this bivalve, the bivalve will not allow these epizoans to block its posterior commissural line. As you can see, there are epijoan attachments, that is the bivalve allow the epijoans to settle in the posterior portion of its shell, but it is not allowed to the epijoans to completely block its posterior commissure line. Although there are epijoans, although there are barnacles in the posterior portion, but the bivalve is able to open its posterior commissure line so that it can maintain contact with the external environment. So only if you get these kinds of epijoan attachments in the posterior side of the bivalves, you can have, or you can say that these attachments occur in the bivalve in the living condition. Now if suppose if this kind of semi-infaunal bivalves are dead, so in the dead shells they are removed out from the sediment cover and they oriented differentially. So now in the dead shells all the surfaces are available to these barnacles, to these epizoans, to attach themselves in the dead cells. So in the dead cells the attachment may be in the posterior side, the attachment may be in the anterior side, maybe in the dorsal side, maybe in the ventral side. Even if the dead cells are toppled, the attachment may occur in the insides of the bivalve or insides of the valve also. So the occurrence of barnacles, that is in which side of the shell the barnacles occur, and also in presence of barnacles, in presence of these epijoan attachments, is the bivalve able to open its two valves. That indicates, or with the help of this we can say whether the attachments occur during the living condition of the bivalve or the attachment occurs after the death of the bivalve. Now, when we have to make any comment about the mode of life of the bivalve, only when you get these kinds of epijoan attachment in the posterior side of the bivalve, then only you or one should able, one can tell about the semi-infaunal mode of life. Otherwise, this bivalve specimen without any epijoan attachment, as you can see in this picture, they are exactly similar to the shallow burrowing mode of life, that is completely infaunal, shallow infaunal mode of life. So without getting any barnacle attachment, it is better to uh, comment on the mode of life of this bivalve as shallow infaunal or shallow burrower. Next group of bivalve having deep burrowing mode of life. Now, in contrast to the shallow burrowing mode of life of the bivalve, these bivalves are equivalve, but they are strongly inequilateral. The muscle scars, the adductor muscle scars, they are dimerian and strongly anisomerian. As the bivalve stays in deeper part of the sediment, so it requires a long siphon to keep contact with the fresh water. So thereby they require a deep pallial sinus within the shell for place of this long siphon. The shell is thin, that means their shell thickness is low. They are compressed, that means width of the bivalve is low, because they have to penetrate, they have to go deep inside the sediment cover. If it is high width, then to go deep this much amount of, for digging this much amount of sediment, they require much energy and they have to dislodge, they have to uh, create space for their position, they have to remove a lots of sediments. So instead of that, to minimize its effort, to minimize its work done, it basically compressed itself, that is lowered its width and becomes streamlined, becomes anteroposteriorly longer, so that it can easily penetrate within the sediment cover. So that is the streamlined shape and compressed, that is low width shape, they indicates that the bivalve is living in a deep infaunal condition, that is deep within the sediment cover. And as the bivalve lives in deep conditions, in deep inside the sediments, so at this position, the bivalve is not allowed frequently or not able frequently to open or close its valves for requirement of food or for expel its excreta. So thereby they have a permanent gaps at both ends to remove its food and to remove its siphon. So they have pedal gap, permanent pedal gap and siphonal gap, so that when the valves are closed, still there exists some opening from which the food and siphons can be go out and maintain contact with the outer environment. So if these in cell characters are found within a bivalve specimen, we can say that the mode of life of the bivalve is deep burrowing. Here you can see these are streamlined, that is anteroposteriorly long shells, permanent opening. Here you can see the siphon. In this angle it is foot. Here you can see a distinct gap, although the valves are closed, but they are remain, that means in this portion, in this anterior and in the opposite side, in the posterior portion, the although the valves are closed, but there remains a permanent gap for the passage of food and siphon. Here you can see the siphon is out from the shell, although the valves are closed, and this is the food. So there, in for deep burrowing bivalves, there must have a permanent gap in both anterior and posterior direction. The third type of mode of life found in the bivalves, that is the epifaunal group, and here it is the bisally attached. That means they have some threads, they have some byssus. Here you can see in this picture, these are the threads by which they basically attached themselves to the hard substrate, because they are epifaunal. So the waves, any kinds of currents, they basically topple the bivalve, they basically they can dislodge the bivalve from its original position, and sometimes it may be fatal to the bivalve. So to prevent the disorientation of the bivalve specimen, it has to fix it with the hard substrate, and thereby they have some byssal threads by which they can be firmly attached with the bottom hard substrate. Now, what are the cell characters by which we can identify this mode of life? In this case, cell is also elongated, although it may look somewhat triangular in shape, but the cell is elongated along the anterior posterior line. Commissure plane or sagittal plane is vertical. Anterior is highly reduced, and the beak shifted to anterior portion, anterior margin. Generally, we know from the bivalve morphology that the beak occurs in the dorsal part, but in this bivalve, beak shifted in this anterior margin. Venter is flattened with a byssal notch at the middle. This byssal notch, basically byssal threads are soft organs, so after the death of the organisms or in the fossil specimens, we cannot see the byssal threads, but the position from where byssal threads emerge and attached with the hard substrate, at that position a notch or a depression is there, which basically confirms the positions of byssal threads from, that is the positions of byssal threads from which it emerged inside the cell. That is the byssal threads came out inside the cell at this condition, at this position, and they fixed with the bottom substrate. So This notch is basically an indirect evidence of the presence of byssal threads. Now, along with the notch, the ventral side is also becomes flattened because it is an epiphonal, it has a chance to dislodge its orientation. So thereby the bivalve lower down its center of gravity, and for that it has to bring more mass towards the ventral side. That means the um, ventral side becomes more wider, that is the ventral side is more flattened so that it prevents dislodging or it prevents disorientation during any kinds of high energy condition. These bivalves are strongly anisomerian. They are dimerian, but the anterior muscle scar is highly reduced. As you can see, this one is the posterior erector muscle scar, and the anterior erector muscle scar is someone in this place, and it is highly reduced. Muscle line and hinge line make acute angle. As I already told you that this is an epiphonal bivalve, so the muscle line and hinge line always cross cut each other. So if these characters satisfy, we can say that the mode of life of the given bivalve specimen is epiphonal and bisally attached. Now you can see the same epiphonal bivalve having bisally attached with the bottom substrate. It has two muscle scar. One is here, the larger one, that is the posterior one, the smaller one, that is the anterior one. These are the bisal threads by which it can epiphonally attach with the substrate. Now, these bivalves some modifications when their relatives goes inphonal. So during uh, evolution from these epiphonal bivalves, when they goes inphonal, when they becomes inphonal, for that new environmental condition, for that new mode of life, with this bisal uh, attached, with this bisally attached um, internal structure, internal form, internal shape, internal musculature, they have to go a little modifications. So as you can see, this is one bisally attached epiphonal bivalve, and gradually it goes inphonal, but at the same time it also remains inphonal. It also remains bisally attached also. So what are the changes when a bivalve is epiphonally bisected and when a bivalve is inphonally bisected? Here you can compare. This one is epiphonal bisally attached bivalve. This one is inphonal bisally attached bivalve. The first thing change is the interior shell morphology. So the positions of the musculature, the position of the adductor muscle scar, the position of the bisal glands, these are changed. And also you can see that the in case of epiphonal, as we already learned, the hinge line and muscle line makes acute angle. But in case whenever it is inphonal, it goes inside the segment, you can see that the hinge line and muscle line are almost parallel. Second, the musculature also changed. As you can see in this picture, here the anterior one is much smaller in size, almost absent to very negligible in size, but here the anterior muscle scar is uh, sufficient or suitable in size. The life position and feeding currents also change as it is an in epiphonal. Here you can see the feeding currents come in this direction and removes the excreta in this direction. But as when it becomes inphonal, the life position is changed. The direction of feeding currents and the excreta rich water, that will also change. The next is bisal retractile forces. As you can see in the by these arrows, the direction of cell forces by which it can maintain its balance, and the bisal threads, they are emerged and sometimes they are retracted. That forces directions that with respect to the orientation of the cell are also changed. Now another major change found in the external morphology of an epibysate, that is epiphonal bisally attached bivalve, and an endobysate, that means infaunal bisally attached bivalve, is that whenever the bisally attached bivalve is epiphonal, that is lives above the sediment surface, then it has a threat to dislodge or to disorient its position by the by any high energy condition, by any wave activity or any storm like this. So although it is bisally attached, it has bisal threads by which it can attach with the substrate. But sometimes in this slightly high energy condition, it is not sufficient to maintain its life or living orientation. And some more thing, some more morphological development so that it becomes stable in this epiphonal attached form. And for that, the bivalve lowers down its center of gravity. Now, lowering of center of gravity is identified in the bivalve shell by the line of maximum width. You can see that if you draw a vertical line, that is the dorsoventral line, or you can say that is the trace of the sagittal plane. Uh, in two sides of the sagittal plane, there are two valves. So along this line, you can see the line of maximum width occurs more towards the ventral part in all these different genus and different species. Whenever they are epibysate, epiphonally bisally attached form, the center of gravity brings lower down more towards the ventral part, and that is why the ventral side that becomes more flattish. So this flattish ventral side now enhances its stability to maintain its erect living condition in the um, or above the sediment surface. In contrast, when the bivalve when these kinds of bisally attached bivalve becomes infaunal, then they don't have any fear to dislodge its orientation, because already it is within the sediment surface, and from that dislodging or disorienting it is little difficult. So thereby the bivalve did not make to lower down its center of gravity. The bivalve did not need to lower down its center of gravity. So you can see for the endobysate bivalves, the line of maximum width, which is an indication of the position of center of gravity, that is more near the central portion of the height of the bivalve, or sometimes it is more towards the dorsal part of the bivalve. So that is a major modification made in bivalve shape when it is epibysate and when it goes inside and bisally attached. So when it goes inside bisally attached, its ventral surface is not at all flattish, but when it's um, epiphonally bisally attached, its ventral surface overall compared to this form is more flattish, and that enhances its stability in the um, external portions of the sediment surface, and to help them to prevent its disorientation or dislodging in slightly high energy condition. Now the next like form, that is, in this case these bivalves are secreting some calcium carbonate, by which one valve of the bivalve specimen, they are attached with the hard substrate. That hard substrate may be a piece of stone, that hard substrate may be a rock, or sometimes it may be a tree trunk also, in which these bivalves are found to be attached permanently. So they are permanent in their position, they are not able to move from one place to another place. So that means they are sessile. Now the characteristics of these kinds of bivalves are, here the two valves are strictly unequal. So this is the first mode of life we found in this presentation or in this discussion, when the two valves are strictly unequal. Now the size of the two valves depends which valve is interacting with the environment. That means if the two valves interact with the environment equally, then their size should be same. Whereas when the two valves interact with the surrounding environment in different degrees, then the valve which interact with the environment more, that will be of bigger size. And in this case, it is the left valve or the lower valve which is basically interacting with the environment more by attached itself, by attached this lower valve or left valve firmly with the hard substrate by cementation. So thereby this lower valve or the left valve is larger in size and the upper right valve is relatively smaller in size, and basically it acts as a lead over this larger left valve. Shell is strictly monomerian, that is they have one single large adductor muscle scar. As you can see in this picture, this one is the position of the large single adductor muscle scar, and this single adductor muscle scar is occur slightly posteriorly. There are numerous attachment scar or cementation scar found on the valve which is attached with the hard substrate. For this group of bivalves, uh, the attachment occurs with the hard substrate in the left valve. So lots of cementation scars or attachment scars found in the lower left valve. As these are cemented with a hard substrate, the shell is irregular. They did not have any specific shape. They have a very diverse in shape. Now, in terms of evolution, there is a distinct or there is an interesting fact that all these kinds of monomerian bivalves, like the cemented bivalve and the uh, next discussed group of bivalve, that is the free lying bivalve uh, or swimming bivalves, in terms of evolution, they came from a bisally attached ancestors. And as you can see in the previous in the previous slide discussion, that already in the bisally attached bivalves, the anterior muscle scar or the anterior muscle is highly reduced. Now during evolution, as these bivalves evolved from those bisally attached form in which the anterior muscle is highly reduced, so in these kinds of bivalves, it is the cemented, the free lying, the swimming bivalves. Here, uh, the anterior muscle scar is completely gone, and instead of anterior muscle scar, only the single large posterior muscle scar remains. So that is why most of the epiphonal bivalves, that is the cemented bivalve, free lying bivalve, or swimming bivalve, they are all having single large adductor muscle scar. That is, they are all monomerian. So it is not their choice, but it is the evolutionary path, evolutionary line which guided these bivalves to have these single large muscle scars. Here you can see the oysters, some cemented bivalves. You can see the external surface is very much rough. They have not any distinct shape because this external surface is of a left valve, and it is the valve by which the bivalve is attached with the substrate. So thereby these irregular marks, these irregular scars, they represent the attachment scars along which the bivalve or this particular valve of the bivalve is attached firmly by cementation with the hard substrate. So this presence of this attachment scar is an important tool or is an important feature by which we can identify these epiphonal cemented bivalves. Here you can see a colony of cemented bivalves. Uh, Lots of bivalves you can see. This is the larger left valve. You can see the muscle scar, large adductor muscle scar, and over this large left valve, cemented valve, the right valve act as a lead. In this case, the right valve is somehow dislodged, somehow disarticulated, but you can see these portions in these cells. Here, the left valve is larger and the right valve is just covering the opening. So it acts as a lead, and it is, as it's interact with the environment much less compared to the lower left valve. So thereby its size is relatively low compared to the lower left valve. The next mode of life to be discussed is the free-lying bivalve. So these free-lying bivalves has exactly same morphology like the cemented forms. That is, they are also highly unequal valves. The lower valve being larger, the upper valve act as a lead. It is also monomerian, that is a single large adductor muscle scar which also occurs slightly posteriorly. They have slightly incurved beak. This incurved beak, because we know that it is the beak or near beak condition where the dentition occurs, and this is the place where the two valves are attached. So in this condition, now this, as they are freely lying, freely occur over the sediment surface. Now as in the basin there are continuous sediment supply, so with time it may happen that the bivalve gradually sinks down. So after some time, it may happen that the bivalve completely covered up by the sediments. So by natural way, it face death by simply sinking down in the sediment cover. So, and when the sediments deposited along the commercial line, then bivalve will not able to open its two valves. So thereby to prevent it, the bivalve have incurved beak, slightly elevated portion and then turned. So due to this incurved nature, now it is not allowed to freely settle sediments in these uh, areas where the two valves are joined inside. That is, they are not uh, allowing fixing these beak surrounding areas so that they can easily open the two valves and take fresh nutrient rich water and expel the excreta. The main difference or the main morphological character by which we can differentiate out these kind of free-lying bivalves from the cemented forms, that they did not have any kind of attachment scar in their external surface. All the cemented form, as they are firmly attached by cementation, that means this secreting some kinds of calcium carbonate which is used as a cementing material, and by using that cementing material they are attaching their left valve or lower valve with a hard substrate. But in this case, as they are not attached with any kind of hard substrate, they freely lie over the sediment surface. So they did not have any kind of attachment scar or cementation scar in the external surface of the larger lower valve. So any kinds of highly uh, unequal valves bearing bivalve, that is the bivalve having two unequal valves, monomerian, and no attachment scar, that indicates a free line bivalve. Here you can see a colony of free lying bivalves. The two unequal valves are clearly observed. And this picture is from the South India, from the Cretaceous deposits of South India. Next is the swimming bivalves, that is those bivalves who can freely swim. In this case also valves are unequal, but here the change from the previous cemented and free-lying mode of life is that here the larger valve is the right valve. It is the lower valve, and this right valve is relatively larger in size compared to the left valve. So in this case, left valve act as a lead over the larger right valve. Here for swimming bivalves, they are also have single large adductor muscle scar. That means they are monomerian, and it occurs also slightly posteriorly. In addition, they have two ears, that is they have two auricles in the two sides of its beak. They have obtuse ambonal angle, shell is lowly convex so that it becomes effective hydrofoil. Now, what it did when it's tried to swim, you can see another picture of a swimming bivalve. The difference you can see in these two pictures, in this picture the auricles are of same size, whereas in this picture these two auricles are of different size. Now why they are so? Here you can see a swimming bivalve is in its swimming condition. Now how it swims? As we know, in this dorsal part near the beak, the bivalve is attached, the two valves is attached with the dentition pattern and with the ligament. Now, during swim, the bivalve opens its two valves and take water along its ventral margin. Now, when it have to move, it takes water along its ventral margin and expels the water at the side of or from these two auricles. So with high speed, they in, eject out or they expel their water along the auricles in the external water body. So that creates a jet by which the bivalve moves in this direction. So they take water from the ventral side and they forcefully they creates or they eject they expel the water in high speed to this water body in from this auricle portions, and that creates jet, and that will help the bivalve to move in the opposite direction of the jet. So jet is in this direction, the resultant jet, so that bivalve move in this direction. Now you can see, as I told you in the previous picture, that in this case the two auricles are of similar size. Here the two auricles are of unequal size. Now why this is true? In this case, this bivalve is a free swimmer, that is it is a very efficient swimmer. Now apart from these two equal sized auricles, there is another property or there is another difference in between these two bivalves. If you look at the length of these two bivalves, in this case the anteroposterior length is greater than the dorsoventral length. But in this case, the dorsoventral length is greater than the anteroposterior length. Now, when the anteroposterior length is greater, that means it has a much aerial span in this anteroposterior length, it becomes more hydrofoil. That means it becomes more effective, or it is more able to float within the water body. But when this dorsoventral length is greater and it has much shorter aerial expansion along the anterior posterior line, it is not very efficient hydrofoil to float within the water. Also, the two unequal sized auricles, due to these unequal sizes, the jet in these two directions are different. And basically, this type of unequal size of auricles presence indicate some additional features, that is, in the anterior portion, below the anterior auricle, you can see and a notch. This notch is basically a byssal notch from where byssal threads is attached. So basically, this bivalve is a byssally attached bivalve, and the byssal threads emerge um, for this bivalve from this below portion of the anterior auricle, and when it swims only when it feels threat. So basically, it's a free lying or epiphonal byssally attached bivalve, and it occasionally swims when it feels threat. So that is not a very efficient swimmer compared to this one. This bivalve is a free line, and it is more efficient free swimmer, which is identified by its greater anteroposterior length than the dorsoventral length, presence of two equal size auricles, and also the umbonal angle is obtuse. In this case, the umbonal angle must be acute. Now, why the aerial span along the anteroposterior length of the bivalve makes it more efficient swimmer? You may be very well aware of this person. He is Michael Phelps, the famous Australian swimmer. At the age of 31, he claimed 28 Olympic medals, and in a single Olympic, that is in 2004 Olympics in Athens, he achieved uh, six golds. Apart from that, there are silver and bronze medals also. So that is the highest gold medal claimed by an athlete in a single event or in a single type of play happened in the Olympic Games. Now, why Michael Phelps is so efficient swimmer? When people try to explain it scientifically, they found that if the length of Michael Phelps are measured from its head to the bottom portion of its foot, and from its aerial span, that is when the hands are up, and if we measure the length from this tip to this tip, we can people find this this length, this span is greater than the anteroposterior or than the height of Michael Phelps. So that make Michael Phelps more efficient hydrofoil, more efficient floater. Same is the case for a bird also. Bird's wingspan is much more higher in length compared to its anteroposterior length. Same is the case for a aeroplane. If you measure the length from one wing to another wing, that will be much higher from its anteroposterior length. So whenever the aerial span, that is across height, across anteroposterior height, is larger, in case of humans, this is the height. In case of birds, that will be the anteroposterior length. In case of planes also, that will be the anteroposterior length. That is shorter than this aerial span, then this across height or across anteroposterior span is greater than this one. It makes the person, or it makes the organism, or it makes the object more efficient hydrofoil. Similarly, for bivalves, this will be the dorsoventral length from beak to ventral side, and this will be the anteroposterior length. So as in case of swimming bivalves, The anteroposterior length is larger than the dorsoventral length. That makes it more hydrofoil, more efficient floater. So that brings the bivalves more efficient swimmer. Now the last group of bivalves, or the last mode of life found in bivalves, that is the burrowing or nestler bivalves. That is, these are also infaunal bivalves. So like the infaunal deep burrowing bivalves, they are also elongated in shape and streamlined or cylindrical in shape. Cell is thin, resistant to abrasion. Anterior edge is provided with stout spines because they have to bore within a within a hard rock, because as they are bored, there is a fundamental difference from the burrowing groups. The burrowing groups dig their burrow within the soft sediment, within the unconsolidated sediment, whereas these the borer groups, they bore or they make their passage within the hard rock. Now, how they bore? They create some kinds of acid from their anterior margin, and also there are some kinds of spines. There are some kinds of tools in the anterior margin. So, by secreting acids, they basically dilute the rock material, and by using these kinds of spines, sharp, stout spines, they loosened up the rock material and create space for themselves. So these spines basically act as a scraping tool for these kinds of bivalves. In contrast to this borer group of life, the nestlers are also occupying the environment in a hard rock, but instead of physically boring, physically make space within the hard rock, they use an existing cavity. So all if there is already any cavity within the hard rock, these kinds of bivalves, they use them with making slight modifications. So often these kinds of bivalves, these borer and nestler bivalves, they are found preserved in their own domicile. That is, they are found dead and found fossilized in their own shelter, in their own home. So, like the deep burrowing bivalves, deep infaunal bivalves, they are also elongated, cylindrical in shape. They are also strongly anisomerian muscle scars, and the hinge line and muscle lines are almost parallel. Shell is thin but resistant because they have to penetrate, they have to go inside within the hard substrate. If the, if the cell is not so resistant, then there was a chance that during boring and the cell becomes fragmented. So at that time the bivalve suffers death. So to prevent it, the shell material or the crystal structure of the bivalve be so that they can resist the abrasion. The anterior edge have some stout spines which acts as a scraping tool with the help of some acid secretion into the hard substrate, and by that they make their passage. Apart from that, as you can see, these are the spine like structures in the anterior portion by which they can scrap. Apart from that, often some extra calcareous material is found covering the ambonal region, because it is found that the ambonal region of the bivalve, of any kind of bivalve, is the thinnest portion of the bivalve. So during during boring within the hard substrate, this ambonal portion, and also we know that this ambonal portion is the most convex part of a bivalve shell. So during boring, this ambonal portion, they face more scratching, more erosion more friction with the external hard substrate. So it may happen that with continuous friction, with continuous rubbing of this ambonal portion with the hard rock, the ambonal portion becomes eroded and there form a hollow. That means this ambonal portion becomes fragmented. So if it is happened, the bivalve suffers death. So to prevent these kinds of erosion in the ambonal region, some extra calcareous material was secreted by the organism, which basically covers this ambonal portion to protect it during its insertion within the hard rock. So presence of this extra calcareous material protects the ambonal region from the friction with the hard substrate. So this is also an extra material which is only found in boring or nestling group of bivalves. Here you can see the boring and nestling group of bivalves. Here you can see all the um, borings or all the hollow openings within a hard rock. You can see two bivalves are preserved within their borings. Here you can see the bivalves are within their cavities in the mud rock. That is a recent rock, and it is a mud. And now, as mud is a soft sediment, but the cohesiveness of mud is as very high, so often mud acts as a hard substrate, and the bivalves, which makes its passage, which makes its shelter within this mud substrate, they have almost similar morphologies like those which make their shelter in these hard rocks. So, in terminology, um, these bivalves which make their shelter in the mud, they are known as mud borer, and these are known as rock borer. So just to distinguish them, whether they are uh, whether they are boring in the soft sediment or whether they are boring in the hard rocks. So in conclusion, it can be said that from the above discussion of cell morphology and mode of life, it is clear that the shape and general morphology, that means the nature and size of muscle scars, their orientation, position of muscle scars, depth of pallial sinus, nature of commissure line, that have much adaptive significance to the mode of life, and that their orientation or their position, their shape has changed with respect to different environmental conditions in which the bivalve lives. That means they are changing with different mode of life. In contrast, dentition, hinge structure, cell mineralogy, the microstructure, that is the crystal orientation within the shell in different layers, they are very stable characters, and they are not affected to different mode of life. Instead, they are used for higher order classification. In nature, it is found mostly bivalves are equivalve and symmetrical only when the two valves are interacting with the nature, with the environment equally, like those in case of burrowing, in case of boring, or epiphonal or infaunal Byssated bivalves. But this symmetry or this equivalveness nature is disturbed or is lost whenever the two bivalves interact with the environment unequally. That is the case for cemented, free-lying, and swimming life modes. In these cases, the lower valve for cemented and free-lying bivalve, the lower valve is the left valve, whereas for swimming bivalve, the lower valve is the right valve. So here, for these three groups, the lower valve interact with the environment, and it therefore becomes larger and slightly more convex. The upper valve becomes highly modified and it only acts as a lead over the larger left valve. So that's all. That's a brief introduction about the life mode of bivalves, different mode of bivalves found in nature, and how these different mode of lives force the bivalves to make some morphological changes, to make some adaptive changes, so that the bivalve becomes a successful one and successfully live in the different environmental conditions by uh, accepting different mode of life. Thank you.